Good morning, everybody. Welcome to another beautiful Science Saturday. Are you guys excited?
Of course.
I am so excited. So, hey, it's Kitty. I was told recently that I don't introduce myself in the beginning of Science Saturdays.
Who doesn't know who you are?
I know, right? We know who I am. So, I am Kitty. We are doing Science Saturday today at the University of the Virgin Islands because it is such a great place to host, to do science. And I'm joined today by our favorite scientist, Joe. Hey.
Right.
And Science Saturday intern, Mason. Good morning. All right. So, we are doing some extreme sciencing today. In case you didn't notice the setup,
Across the board.
so much science going on. But before we get into that, I have a little bit of news to share, which is going to explain why we chose this so far ambiguous topic. Unless you read the description, we're looking at pH. So our favorite scientist, Joe, is moving on to become a bigger and fancier scientist and is going for his PhD.
Mhm.
Yay! And so Joe is moving to Puerto Rico. Boo.
We like Puerto Rico.
We do. We like Puerto Rico. So Joe is moving to Puerto Rico to get his PhD. And we're going to learn a little bit about one of the concepts in his research. So guys, I'm going to pass it over. I'm going to get behind the camera today. Weird. I know. I'm in charge of tech. And Joe and Smush are going to be doing all the science. So while I run to the other side, Joe, why don't you tell us a little bit about what your research is going to be like and why we chose pH for our topic today?
Yeah, thanks, Kitty. Yeah, so here, I'll scooch over this way so we can kind of spread out a little bit. So, when it comes to pH and why we chose this topic, even though we're not in the water as much as we love to be in the water, pH is a really relevant topic to a lot of what we do, and in particular to coral reefs. Now, coral reefs, as we know them, right, they're really important for wave-breaking energy. They build these massive structures, create homes for fish. Well, all that actually relates back to this concept of acids, bases, and the pH scale. So, Mason, we were talking earlier. Are you familiar with what exactly is the pH scale?
A little bit.
A little bit? Yeah, I think a lot of people might not know, but might have heard of things like, I think we all know acid, right? You know, it's something like we can use for like cleaning, or, you know, but it can be kind of harmful, right? You don't want it to touch your skin or things like that.
Yeah.
So we've heard of acids in that way. You ever heard of bases in terms of like on the pH scale? You've heard of bases before, right?
A little bit.
Guitar bases and, you know, bases of in a sound system. No, we're not going to talk about those today. We're talking about bases are essentially the opposite of acids, right? And so when it comes to acids and bases and exactly what they are, I wanted to back up and talk about that, and then we'll get a little bit more into why that's important in the ocean. And that's where you hear things like, some folks might have heard of something called ocean acidification, right? Where the ocean is getting more and more acidic, which it sounds pretty scary, right? You know, like we don't want to go swimming in acid, right? Well, it's not quite like that. And so we can explain a little bit more about that in a little bit. So let's start first by, we've got lovely scenery here. Hopefully you can still hear me. I wanted to start off first by just kind of giving a demonstration of what is an acid and a base, right? And what this actually all relates to is what is water. So from a science perspective, what's water?
2 parts hydrogen, 1 part oxygen.
Right, H2O, right? That molecule, two atoms of hydrogen, 1 of oxygen. Perfect. So to represent that, I thought, since I don't have any full-scale H2O models on me, we've got plenty in here. This is some water that we've got in the beaker here. But I just thought I grabbed some pennies and nickels, and I thought we could use those. So how about, let's say, I'm going to put these on the table here. And let's say that pennies represent hydrogen and nickels represent oxygen. So if you were to build an H2O molecule, why don't you go ahead and build one, Mason? So you got the 2 pennies, the 2 hydrogens, you need 1 nickel. There you go. Exactly. And we can keep building a couple more of those, right? So, and actually just fun fact about H2O molecules, they're actually kind of bent like this. They kind of go one on either side, right, to make it balanced. And so we've got plenty of H2O molecules we can build here, right? And they exist together. That's a a chemical bond that they form and keeps them attached to one another. Now, and this is what we learn a lot about when we're first learning about chemistry and the science behind like water molecules and things. Now, when we talk about acids and bases, what's really interesting though, and here I'll keep these off to the side right now. So we've got all of our water molecules, and so this is what we kind of envision a glass of water might look like, but a lot more of these.
You spilled water on my table.
Oh no, there's water everywhere. But but what's interesting is actually when it's water existing as a liquid, it doesn't necessarily look like this. If you were to zoom way in, and our camera can't quite zoom all the way in, but what it actually looks like is when water is existing in what's called aqueous solution. It's as a liquid. It'll exist as not these single molecules, but separated out with an oxygen and a hydrogen by itself. So if we were to zoom in onto a glass of water, we'd really see something more like this.
Ooh.
And so you have your hydrogen atoms by themselves, and you have OH, oxygen and hydrogen, by themselves.
So I have a question.
Yeah.
Are these standalone guys like connected to that somehow emotionally or chemically?
So the way to think about it is like this one is connected here, but it might drift over to here, and it might drift over to here. So while they're not separated, right? You can't just go in and scoop out hydrogen out of a water glass. They're not necessarily sitting right here next to the oxygen, right? So they're kind of moving freely, and so you can imagine this one might go here, and this one might go here, or maybe this one will go down here, and this one will go up here, right? They're all kind of sharing these hydrogen molecules, or these hydrogen atoms.
Sharing is caring.
Right, of course. And so the other point about this is hydrogen, when it's by itself as a single atom, and it's not a part of this bond, is positively charged. It has a positive charge, right? You think on a battery like a plus, and that's because when the molecule is all together, it's neutral. There's no charge on it. But when they're separated, this hydrogen ion takes all the positive, and this OH, oxygen, hydrogen, takes all the negative.
Oh.
And so what we call, whenever we have these molecules or these atoms that are charged, we refer to that in chemistry as ions, right? Ionic. I mean, ionic basically means that there is a charge. And so when we talk about hydrogen, we'll talk about ions, hydrogen ions. So you think of this is a little plus. I should have found pluses and minuses. So we have all these little pluses in the water. And so what we're talking about with what pH is, and that's kind of a weird term, right? What we're talking about is we're actually saying how many hydrogen ions are in the water. That's what pH is. It's just how many hydrogen atoms are in this water. And so you can imagine, right, remember, because these are sharing.
Probably going to be a pretty big number.
Yeah, it's a pretty big number. So we reduce it down to a scale, right? But you can imagine, like, with these sharing, it'll probably be pretty balanced, but it doesn't have to be, right? So we have all of our OH and our H molecules, and so if we were to separate them out, and these would all balance to one to one to one to one. But another way that this liquid can exist is if we took away one of these, and one of these H's just bounces between two. So now we have less hydrogen than we do OH. So the concentration of hydrogen has lowered, right? So, and then you can think of it a similar way if we add a whole bunch of pennies. So now we have more hydrogen than we need. And so we've changed the concentration of hydrogen atoms that are in the water.
That's crazy.
Still water.
Still water.
Right?
Just
and so
extra H's.
Right. And so when scientists were building this pH scale, they really centered it around water. And so the water as we know it, that we know and love, that we like to drink, that is right in the middle of our pH scale. From 0 to 14, 7 is water. And that means, essentially what that means is when you're at 7, that means you have exactly the right number of hydrogen pennies to OH or oxide ions. So it's perfectly balanced. That's 7. That's water. That's what we know it. If we have too few hydrogen atoms, so there's more sharing going on, that's when we've got what's called a base. And anytime we have too many hydrogen atoms, there's extra hydrogen atoms we don't need, that's what's called an acid, right? So, and this is all happening at the microscopic scale, and it's all about how much hydrogen is in the water. And how much hydrogen is in the water affects a ton of what that liquid can then do, right? So that's where we get our pH scale. And you know, you hear a lot about, like in media, like you think like action movies and things like that, people talk about acids, right?
Yeah.
So like, what do you think about with like acids?
It's like an acid gun, or like using like a beaker of acid to like dissolve like
Right.
some metal or something.
Right, it's gonna burn, right? It's gonna dissolve something, right? So I think it's really interesting because when we're at our perfect balance of pH of 7 water, water is what's referred to by chemists as the universal solvent. And that's because it's just about the best at dissolving everything, right? And we use water to dissolve things all the time. Think like instant coffee, or you know, like maybe like the sugar or Splenda, right? We dissolves that into the water. Alka-Seltzers dissolve into water. Just about everything dissolves in water. Some stuff doesn't. And so some stuff dissolves better in acids, where you have that extra hydrogen to kind of pull things apart. And some stuff dissolves better in bases, where you have less hydrogen, but you have more of the negative hydroxide ions to pull things apart. And so when we talk about acid, generally speaking, we talk about things that, like, you know, dissolve stuff. Well, it dissolves certain things, but it doesn't dissolve other things, right? And the other thing is, there are acids and bases around us all the time. So we've got a whole bunch of stuff on here. All of these are more acidic and or more basic. And a lot of these things are things that we see every day. So I've got a couple examples here. I've got vinegar. Now we might not have this like straight all the time, but we use it a lot in what we cook. You can use it in cleaning and things like that. And we kind of took the time before this to kind of sort them by, you know, basic to acidic. So we've got our water right here in the middle, so you can imagine that, our pH 7. We've got, I'm going to come back to this, this is our cabbage juice, our pH indicator. We're going to talk about that in a little bit. We have clementines, some of my favorite snacks. These and a lot of citrus, it tends to be more acidic. And you think of like that kind of sour tartness, right? Kind of a more acidic taste, right? Vinegar, again, you know, we can use here. I've got in here a lot of people's favorite beverage, coffee. We're gonna find out how acidic coffee is in a little while.
Cool.
And then kind of at the top end here, I've got lemon juice, concentrated lemon juice. So this is among one of the more acidic things that we know about, right? And of course, there are things that are even more acidic. I didn't want to bring those things out today.
We're not melting holes in any metal.
Right.
No supervillains today.
Yeah. Can't have that on Science Saturday. So now we move towards the more basic. We're gonna come back to this. This is some Tums, but this is a little bit more on the basic side. But in our liquids, I brought some boxed milk. So milk is a very common base that we generally consume and have. And then just to kind of go on the very extreme, I have chlorine bleach, just because that's something I know is very common in homes. And a lot of people think because it's very caustic that it's an acid. It's actually one of the most basic. It is a very strong base that we use as a disinfectant.
Okay, I have a question.
Yeah.
So we've got acidic,
Neutral.
neutral, basic. I'm seeing cooking in my head because surprise, surprise, I'm a little hungry. And Joe has coffee on the table that I'm not allowed to drink. But I'm thinking about combining these things. So people take their coffee and put milk in it. To make a lot of recipes, you take vinegar and add something kind of milky.
Right.
So I'm just thinking about like the combining of those, like us trying to achieve the neutral.
Right. So I mean, we're talking chemistry here, but chemistry is never far off, and Kitty and I both know this. Chemistry is never far off from cooking. So
It's always almost lunchtime.
right. And so, you know, when we talk about when we're in the culinary world, a lot of that is balancing acidity and balancing more basic flavors. And so, you know, this is what we were just talking about, right? These more citrusy, these more sharp flavors, that's kind of how I think about it. Those tend to be more acidic. And you don't want too much of that, but you want a little bit of a bite, right?
Mm-hmm.
Yeah.
And then you've also got, you know, much more savory flavors, things like milk or not quite. Not quite. I don't think that's not quite in culinary. That stays pretty squarely in chemistry. So so now we know, you know, generally speaking, what you know, acids and bases are, right? Why don't we talk a little bit about how we measure it?
Ooh, yeah.
Right? So like we know all about these things, and these obviously are not all the acids and bases, and so one thing we can talk about is how do we find out what's acidic and what's basic? We can't go down and count the atoms like we can with our pennies. In fact, why don't we go ahead and get these cleaned up for now, just because they're not really acids and bases. We'll make way for the real acids and bases. Let's put them back over here, and we can always come back to that, right? So that's what brings us to our most chemically important giant beaker here of purple liquid. Now, as we finish this up, so now this is something that I prepared before here, but you can actually prepare at home, either you or you know, with your parents or something like that. All I did is I went to the store and I got red or purple cabbage, and I brought water to a boil and I chopped that up and I put it in here. And so in red cabbage specifically, there's a compound that boils out, comes out of the water, leaches out, and it turns this dye purple. But this purple dye actually changes color depending on the pH that it's exposed to. So right now this is just in water, right? So you can think of this is it's just purple water. But if we expose it to, here, you want to pour a little bit of that in our test beaker here.
Okay. Science in the beaker.
There you go, just right about there. That's good. So we've just got just a little bit. Why don't you put that back down there? And why don't we, just so that we can see the effect, let's take the strongest acid we've brought.
Okay.
Some lemon juice. Give it a good shake, make sure it's good and mixed up. So remember, what we're doing here, this is mostly, I mean, it's got other things in it, but it's got a lot of extra hydrogen, right? A lot of extra hydrogen atoms. And so we add this to here, we're adding a bunch of extra hydrogen atoms. We're changing the proportion of hydrogen atoms to oxide atoms, right?
Okay.
So when we do that, that affects the color, the pigment that's in this water.
Yeah.
So let me make sure we can see this nice and close. And I'm just going to add just a little bit at a time here. Oh.
What?
So that change, this change in color is how the cabbage juice is a way that you can see, basically saying because of the more hydrogen ions, that changes the actual compound and makes it more of a bright red.
That was so sudden.
Yeah.
Yeah.
Well, that's because this is a very strong acid. We changed the concentration very quickly. One actually interesting fact about acid, the acid-base pH scale. You know, we talk about, you know, going higher and lower. And remember, I said that water has a pH of 7. Well, the interesting thing about the pH scale is that it's what's called logarithmic. It's not, so if you go up 7 to 8, you're not changing just a little bit. You're actually getting double the concentration of hydrogen. And then you go 8 to 9, you're doubling again.
Wow.
And 9 to 10, right?
Oh.
Right. So when we're all the way over here as our strong acid for lemon juice, we're changing a lot of hydrogen. We're adding a lot of hydrogen to that little small concentration, right?
Just wondering, is this still edible, technically?
I mean, all we've done is added water, lemon juice, and cabbage.
Probably wouldn't taste very good.
I don't think it would taste very good. So, but it means that we can kind of put this over here and we can kind of dispose of it appropriately, and maybe we can try something else. So why don't we, let's see. Do you want to try why don't we try one of our bases? Why don't we try the bleach? So here, why don't you do the cabbage and I'll do the bleach here. And now, like I said before, you know, a lot of these things are very safe. You can do in your home. You do want to be careful with bleach because it's one of the strongest bases, and it's one of the strongest liquids that we have today. So you do want to be very careful with something like liquid bleach. And of course, you don't ever want to consume it or anything like that. Okay, so we've got, again, it's very purpley, right? And it looks like it's, if we look at compared to here, because we've already used the the very strong acid. Why don't we try rinsing this out a little bit? It looks like it's still pretty bright, huh?
Yeah.
So here, let's get a little bit more of this and just see if we can just kind of rinse that
Water.
out. We're just diluting it, right? We're just adding more water.
What did you say scientists call water? The ultimate
Solvent.
solvent.
Okay, let's try and put that back in. We'll see if it turns a little bit more. That lemon juice is pretty powerful stuff, so.
I think we're good.
Yeah, so that's a lot better. Okay, so now I'm gonna add a little bit of this bleach. And again, so instead of an acid, now we're looking at a base.
What color will it be?
Ooh, whoa!
Totally different
now.
color, right?
Whoa!
Yeah. Now, again,
What?
this is no longer safe. We do not
Okay.
want, you know,
Yeah.
because we've added bleach, and again, this is a very dangerous chemical. But look how brightly this turns. So again, this is where we started. And this is the color that it changed.
And because we're
little bit.
using beakers, we can see the measurements. We were right around just under 30. What are those, milliliters?
Yep.
And now we're just at like less than 35.
Right.
So not very much bleach was added.
No, not at all. And you could say, like, you know, folks who might have seen bleach normally, it's normally about this color. So this is so strong, we basically only adding 5 milliliters, we've turned this into bleach. Because now this is, I mean, more or less the same same color or similar color to liquid bleach.
Yeah.
Just looks like we've diluted bleach with cabbage water, right? And that's because it's such a strong base, right?
That's wild.
Yep. Now I haven't tried this in a long time, but let's see what happens if we.
Oh.
So now I'm pretty sure with how this works, this should not neutralize, but we can try. I don't think it will. Yeah, I didn't think so. So because
Gone too far.
yes, exactly. And so we would need a much stronger acid. And the thing is we won't.
Oh, I can smell that.
Yeah.
Woo.
So that's a what's called a neutral reaction, where you're bringing things back to the 7 pH scale.
Wash it out again.
Yeah, good idea. So let's do that. And we want to be careful with this again because it still has some bleach residue in it. And we do have another beaker we can use as well. So,
Oh.
well, what do you think about some of these others? Do you want to try any of these other ones?
I personally want to try the milk.
You want to try the milk?
Sounds interesting.
So the milk might be interesting because remember, so milk is what's called a colloid. It means it has stuff that's not dissolved. It's just kind of a part of it. That's what makes it opaque, right? We can't see through milk. So I will say, we might not see as dramatic of a color change just because the milk is a color.
Yeah.
Right.
But it's worth a shot. Let's try it, right? So why don't you add? Yeah, you want to add that? There you go. And just a little bit. Maybe try and aim for only adding to the
20?
or to the 30, which is the little hash in between.
Okay.
So we know that we'll have exactly 30 milliliters, or close to. Perfect. There you go.
And the milk?
Yep. The milk there.
How much milk should we add?
Let's aim for 5, just like the bleach. We'll see if how it does.
I don't know when 5 is. So.
Okay. Ooh.
Yeah. So we are lighting up, some of that being because of the coloring, but
Right.
also some of it being because of what's in milk is it's a much weaker base. So you see that we are lightening this up, moving towards that very dramatic brown color. Though a lot of it is that coloration. So, but there are other ways, of course, we can test pH. Or do you want to try the?
Lavender colored.
Yeah, it is. It's lovely. Do you want to try like the vinegar or the coffee?
Can we do the coffee?
Yeah, we can try the coffee.
very interesting.
Again, coffee is a certain color, so it might not be perfect.
Yeah.
But we can definitely get an idea, and then we can talk a little bit about some of the ways the professionals do pH testing too.
What? This isn't how professionals do pH testing?
That's how I do pH testing.
More lemon juice.
Let's do 2 rinses, just to make absolutely sure. Okay. Let's see what that does. So again, let's aim for 30 milliliters if we can. How's that? How are we at Science Saturday, audience?
Just under 30.
Just under 30, perfect. Okay, I'm gonna try and aim for 5 milliliters of coffee. Though this is not a good pouring spout. Didn't quite have enough beakers.
That worked.
Yeah.
So
Just a little bit of coffee. And so, what color are we saying that is then?
It's like maroon. It definitely doesn't look as like.
It's not the bright red we got with the lemon
right,
juice.
because the coffee's dark, but you're still seeing it, try to change into that red scale
It's
that
still,
we were seeing.
Right, and remember that it's a scale, right? So coffee might not be quite as acidic as lemon juice, but this is showing that it's pretty acidic,
Yeah.
right?
But still delicious.
Of course, right? And so, this is partially where, coffee has that very bitter, that very strong flavor. That's because it's a somewhat strong acid.
Yeah.
So why don't we compare, right? So we already saw the lemon juice. Why don't we compare that to the vinegar? Okay. So in this one, why don't we aim for 30 milliliters in there, and then I'll put about 5 milliliters of vinegar in that, and we can see comparatively what the differences in colors are. There you go. This is a smaller beaker, that's why it's a little bit taller, but still the same amount, 30 milliliters. So you leave it here, we can compare.
Okay.
And so now I'm gonna do the vinegar, and depending on which one is more red, that'll tell us which one is more acidic.
Okay.
Ooh.
That's pretty acidic.
Yeah.
So if we were to look at our pH scale again, we'd probably put lemon juice, vinegar, coffee, right?
Yeah.
We can try these if you want.
Yeah.
Yeah.
Yeah, we might have to take some
Just,
time.
like, squeeze it out.
Yeah, squeeze some out. But first, I want to talk a little bit about some other stuff that we brought here. So this is something that folks might be familiar with. This is spa testing strips, right? And so when you have these, they've got a lot of different measurements. They check all kinds of things that are important to making sure that a pool is looking how you want it to look. But one of them is pH, and you see that while I said that how the professionals do it, it's actually pretty similar to exactly what we're doing here. You're just looking for a color. And so they have special compounds on these little squares that are on them that change, very similar to cabbage juice, a certain color depending on what pH it is. So for example, if we look here, remember pH of 7 generally means neutral and water, right? And then as you go lower, you're getting more acidic, right? And so that's going to turn more yellowish in this case and more red in this case.
And these colors are not going to line up to our cabbage juice changes because that is specific to the purple cabbage.
Right, and this is a different compound.
Right.
But so for example, and again, so for our purposes today, we're just going to look at this top one, this second one here, this which is our pH. So there's a lot of other things that they test on here, but we're just focused on the pH today.
If bromine shows up, we should be concerned.
Right.
And the instructions I read said don't shake it.
So, and I should get out another one so you can see the difference in how the colors changed. So this is on this side, we've got a dry here. So this second one here,
Got red and green and purple.
yeah. So so let's focus on the second one, which is red. So it shows that we're a little bit high, which means we're a little bit basic. And that's expected because actually water, as we know, H2O, the water that we drink, it's not perfectly exactly H2O and only H2O. In fact, we don't want that. We want a little bit of basic, we want a little bit of alkalinity in our water. So it's a good thing that we're seeing that this is going high on the pH scale. And remember, this red is not the same as this red because it's a different compound. And in fact, I just realized it's a little bit extra confusing because we've got, looks like the scale is the opposite on this than it is on ours. But this is showing, so moving from this color to this color means that we have a good amount of alkalinity in our water, or it's more basic. So a weak base, and that's kind of what you want to see. You don't want to see it. You definitely don't want your water to be acidic, right?
No. And
even at neutral, right at 7, can be not really what you want. Yeah. So, and just for a quick reference, we did try. So you can actually use your cabbage juice and turn it into cute little pH strips like this too. After you've boiled your cabbage juice, you can take some index cards. You can put the index cards, you can tear them up into little strips, and you can put it in the cabbage juice and let it dry. And then the compound that's in the cabbage juice will actually sit onto the strip, and you've got your own little strip here. So for example, if we bring back to our vinegar, do you want to dip that in there?
Okay.
And so again, this has that pH indicator compound on it. And so you pull that out, and so we can see how it's picking that up, and it's being very acidic.
Yeah, you can see the color change.
Right. So this is
homemade strips.
Yep, a way to test your pH at home. It's not the most accurate. You're not going to get, so a lot of times these, we're looking for a very small range, right? So like this one really only measures from 6 to 8 on the pH scale. And remember, the pH scale is from 1 to 14. So with things like bleach being down in like 11 to 12, or even 12 to 13, depending on how concentrated it is. So, you know, these strips and these kind of tester things aren't really designed to handle something that's that extreme, but just for a little bit, right? Because we hope that what's in your pool water is going to be like mostly pretty close to 7.
You don't want to be finding out it's outside of those strips.
Right. So now I have one last thing to show us, and why don't we go ahead and get these cleaned and rinsed while we do this. So the last thing I wanted to talk about is, of course, how does this relate to our oceans? Right? Why is this so important? You want to rinse these, and this is where you hear the term ocean acidification. And now we've talked before about the importance of corals and the importance of the structure that they build. And I could spend a lot of time talking about, you know, how they do this, but basically what corals are able to do is essentially pull ions, charged particles, out of the water and turn it into rock substrate. That's how they grow. That's how they build what's called their skeleton, right? And this is what we see when we see like dead corals on the beach or things like that. They're rocks, right? Well, that rock, that specific compound that corals build is what's called calcium carbonate. So it's a very specific compound rock, and they do it by pulling calcium ions out of the water and carbonate ions out of the water, and they create calcium carbonate that's a rock, right? Well, like all things, calcium carbonate, it won't dissolve in water outright, but it might dissolve, but it will dissolve in an acid and not a base. And that's because it's slightly basic, and so the more basic it is, the more it'll kind of exist in the water versus as an acid where it dissolves away, because acids will dissolve bases and bases dissolve acids, right?
Ooh.
So when we talk about ocean acidification, where or let's see, this is where our demonstration comes into play. Basically what is going on is as the earth continues to warm, our oceans are moving just very slightly. I mean, we're not talking lemon juice, but very slightly to be more acidic. Remember how I said water is not, you know, the water as we know it is not very acidic? Well, salt water is also not very acidic. It tends to be a little bit more basic. But as it gets warmer, it tends to move just a little bit more acidic. And so when that happens, the skeletal structure of corals, not the living corals can kind of protect that. But, you know, we have a lot of areas that's just, you know, exposed calcium carbonate rock. That starts to dissolve. It means that literally not only are we losing living corals that are creating shelter for fish and creating structure to protect us from waves, but it's actually eroding away faster. And that's what we really want to look out for. And so one of the questions a lot of people have is, well, how does the ocean get more acidic as the earth warms? So for that, Mason and I are going to function as, we're going to demonstrate that process firsthand with a couple of scientific materials. So this time we're not going to add quite as much. I'm going to add maybe 15 milliliters, maybe a little bit less. I'm going to do the same in my beaker here. Or actually, why don't you take this beaker, I'll take that beaker. Okay. So, we're now going to take our very important scientific instruments here. So, the way that the ocean becomes more acidic is because whenever we use fossil fuels, like driving our car, flying in planes, you know, anytime generating power sometimes, any kind of combustion that creates carbon dioxide, when that's released in the atmosphere after it's done combusting, that concentration then goes into the oceans. And the more carbon dioxide that's dissolved in the ocean, the more acidic, because it basically creates an imbalance that causes more hydrogen ions to be present. So one way that we can do that in our cabbage juice, remember we've seen it turn red when we add more acid. So we can actually add carbon dioxide into this cabbage juice. And that, why? When we breathe in oxygen, when we breathe out carbon dioxide. So if we blow through our straws and we bubble in carbon dioxide into this, we'll see that we'll go, well, let's see what happens, right? And it might take a little bit of time, but let's get some bubbles in there.
Science. Oh man, I feel like I see the color change a little bit.
Yeah, it can take a while, but so maybe just for an example here, I'll go ahead and just leave a little bit out here so you can kind of see the difference. And we can compare to in a second here. So this is with no carbon dioxide in it. This is what it looks like there. And it looks like, see, even Mason's is already starting to turn a little bit.
This is a great angle, guys.
This is where I tell you that you're not supposed to blow bubbles in your drinks, but we're not drinking this, so we can blow bubbles in it.
It's definitely lighter. I see the change. You guys are doing great. Just suspense.
What do you think? Is it getting lighter?
When I blow like straight into it, you can see the bubbles that come out. It definitely looks,
Oh
lot
yeah, you
lighter.
can see the color change there.
but it's very slow. But
It is, and so I mean we're talking very small scale right now, but you can see
Yeah, no, you can see that it's getting a little bit more pinkish.
right. And so this is what is happening in our oceans on a much larger scale.
Right.
Right? The more carbon dioxide that's added into the atmosphere, the more that ends up into the oceans, because the oceans absorbs a lot of that carbon dioxide, and as a result, our oceans become more acidic.
Mm-hmm.
So, you want to keep doing this the whole time? No, we have one more. We have one more demonstration I want to show. Is basically what happens once we've made this more acidic. So, what I've got here, the last thing that I'll show, and you can keep bubbling if you want. Keep acidifying over there. So the last thing that I'll just show, and we'll actually kind of use all of these for easy demonstration, is I've grabbed a very popular stomach cure. This is Tums, or otherwise known as an antacid. So we've learned a lot about acids and bases today. So what do you think an antacid is? If it's an antacid?
not acid.
Not acid. So the opposite of an acid is a.
Not acid. Antacid.
Hey, it's a base.
A base. Oh
Ba-dum,
yeah.
ba-dum, ba-dum, ba-dum. It's a base, yeah. So, essentially, antacids, the way that they settle your stomach. Remember, we know about stomach acid, right? And actually, stomach acid is one of the strongest acids that we know about. It's very good at breaking down a lot of things. But sometimes it can get too acidic, and that's what upsets our stomach. Acid reflux, right? And so when you have too much acid or too acidic, you take an antacid, right? And that raises the pH of your stomach, makes your stomach acid more basic, less acidic, right? And actually, what's interesting is that compound is calcium carbonate. This Tums, this is essentially, with some other things and some other processing,
Oh, there we go.
the same material that coral reefs are made out of. So, just for demonstration purposes, I've crushed up one, so this is what a whole one looks like. And so if we put it into just regular water, remember this water is pretty basic. We drop it into there, and I can even drop a little smaller bit. It's gonna have some reaction, right? But it's generally not gonna be doing a whole lot.
You just see some tiny bubbles on it.
Yeah. So I mean, it's going to slowly dissolve. Remember, water is a universal solvent, so it is going to very slowly dissolve, right? And so that's what's happening if I drop it into, for example, my cabbage juice. Because remember, cabbage juice, we're not changing the pH of the water. We're just dyeing it a color, right? I'm gonna rinse this out a little bit. And so, by comparison, if we maybe put our lemon juice, remember our very strong acid, or maybe why don't we do the vinegar, because that's clear. So we do the vinegar. Again, this was, we saw before, this is a pretty strong acid. So if we put our antacid into the vinegar, you see,
Ooh.
can you see it maybe over top? It's a little easier to see.
It just jumped up.
Yeah, so you see, we'll put another one in there. So you see how this neutralization reaction, right? The vinegar is quickly dissolving that, and that's not what happened. Look, we can check back over on our water here. Not a whole lot happening, right? And same in here. This is again our cabbage juice. We're not changed the pH. Not a whole lot happening in there either, all right? So this is again our strong acid. So now let's compare what our regular cabbage juice to what Mason's been over here acidifying.
Mm-hmm.
And so let's add just a little bit. Why don't we put it right here so it's kind of on the scale here. And so we're just gonna add just a little bit here. You want to add some? You want to add some of these? Just little tiny ones, and put it in there and see. Let's see what it does. So you see already we're getting more bubbles than what we've got on the other side here, right?
This side has no bubbles. This one, it's like
Right.
there's like the bubble pockets all over it.
Right, exactly. So and again, you know, this is a much more subtle change than, you know, our very strong acid over here. But if I had been thinking ahead enough and left maybe one of these in here overnight, you would see that this potentially might even be completely gone, right? This is going to start to dissolve. And then even if we add just a touch, just for effect, or we can even add a little bit from here. Just a little bit in here.
Whoa.
And already we've got more bubbles. It's starting to dissolve a lot faster. So this is what we're talking about when we're talking about ocean acidification. As you bubble in that carbon dioxide and you make the water more acidic, calcium carbonate, corals, or coral skeleton, starts to dissolve. It starts to erode away. And we know it erodes away. Normally, you know, waves and things growing on it start to erode away, but it erodes away much more quickly. And for corals that are still alive, that are trying to build this structure, trying to grow and be strong, that's a lot harder to do when you have to work against a strong acid gradient, right? See, now we see it starting to fizz up there too and everything.
Oh, yeah.
Yeah.
Interesting.
So this is what we're talking about with ocean acidification. And to, I guess, close out and talk a little bit about what I'm going to be studying in my doctorate, this is something that we know is happening, right? And so one of our big question is what can we do at the reef scale to help with this, right? So we've talked about coral restoration before. So is there a way that we can create, you know, corals and coral reefs that are creating calcium carbonate structure, they're creating shelter, creating wave protections? Can we do that by the corals that we outplant? Can we do that by the corals that, or the reefs that we try to restore and build habitat as opposed to just losing it, right? Having it erode away. So I think that was all the demonstrations I have. We didn't have a chance to play with the clementines. Do you want to try those?
Yeah.
Well, we could just
straw in it.
put a straw. Yeah. Well, yeah, we could put a straw through what. Well, here, why don't we peel the tops off here and then we can juice them that way. Well, Katie, do we have any questions from the audience or anything?
We have some comments from the audience, but no questions.
Gotcha.
So I'm going to scooch in here.
Sure. Do you want to help us
And
peel clementines for juicing?
Peel a clementine as we say thank you guys so much for tuning in. We're going to end with a slightly acidic snack, and it's going to be delicious. And we, all of our Science Saturday fans, are so proud of Joe for moving on to his PhD program and the planes going by. And next month, we're gonna have a super special surprise for you. And I'm not gonna say what it is, but we're gonna be in a fun new location, and Joe's not gonna be here. So hopefully the computer works and I don't make a fool out of all of us. So, cheer, cheer.
As always, Science Saturday, we have to have a snack.
Snack time. Here.
Snack. That's a good Science Saturday snack.
These are really good oranges.